各位同学，我很高兴有机会跟大家讲一学期的大一物理。我在80年代、90年代在美国Nobel 大学也教过2次大一物理。我猜想你们的成绩会比 Nobel 的学生好得多，所以你们得当心，因为我预备教完了以后写一篇文章讨论Nobel 的学生跟清华的学生的对比，所以你们也可以说对于清华的名誉负一点责任。我刚才算了一下，是66年以前在昆明念过大一物理，那个可以说是我第一次接触到物理学。那么我希望在这一学期里头，大家不单学到一些物理，还学到一些微积分。这个微积分我要你们特别注意的是这本教科书 Halliday Resnick Walker 的 Appendix 1。这个 Appendix 1里边所讨论的一些公式我希望你们假如你们已经念过微积分，你就复习一下；假如你没有念过微积分，你要注意那些公式。But I also want you to learn some English. I understand some of you would be able to understand my English, but others may have some difficulties. I hope by speaking slowly you could understand most of what I say. But I want also to tell you a very good method to learn English. To learn English, you have to learn how to listen, how to read, how to speak, and how to write. Although those are very different, but there is one thing which ties them together, and that is your own pronunciation. For a Chinese student at the beginning, there's a tendency to be very much afraid to speak because the Chinese pronunciation and English pronunciation are very different. The Chinese language emphasizes the muscular movement of the mouth in the front, like the lips, the teeth, the tongue. In English, the main part of the vocal organs are more backwards. So you have to learn to move the center of attention when you speak from the front of the mouth to the back of the mouth. And how do you do that? There's no better way than to read aloud. So I want every one of you to spend maybe 3 or 4 minutes every day and read aloud. If you practice that for, let's say, for a month, I can guarantee your English would improve. Because, for example, English grammar has many peculiar features which are not understandable to a Chinese student. 我刚念英文的时候，觉得很奇怪，你 I am, you are, he is， 为什么要的更改？ 那么为什么要第三身？为什么多数要加 s？ 这个我当初念的时候，最初觉得这个很不自然，觉得这中国这个是比较自然。可是后来我懂了，它这个所以有这些加 s， 有些inclination， 它的原因是与发音有关系的。所以你如果发音发的好的话，很多文法上的问题 you would understand naturally. Therefore, to try to pronounce things correctly and aloud is very important. For example, you have in front of you this handout. Everybody has that. On the first page is an appendix. I'm going to add to this dictionary. I'm going to add to this dictionary later. But if you turn to the next page, the next few pages are from Feynman's book. So I'll give you an example. If you look at the first paragraph of this handout from Feynman, it's a very short paragraph. You can spend 2 minutes in the morning reading it aloud. In fact, preferably in front of a mirror, because then you can watch yourself. If you have a recorder, record it. After 1 month, you would realize, after 1 month of this practice, if you listen to what you had recorded a month ago, you would realize that you have improved. So this is an important thing. I want you to do this. In the latter pages, no, it's not in it's in the on the web. There is a syllabus, and you should download that syllabus and read that. That is what we are going to discuss in class. Now we go to chapter 1. Of the book, Halliday and Resnick, etc., etc. The chapter is very simple. It talks about the units, and I want you to learn the chain link rule. Every physical quantity has a dimension. It has a unit, except for numbers, for pure numbers. So if I say something is 1 meter long, it is not 1, it is 1 meter. So remember that the physical quantities have a dimension. It has a unit behind it. And the unit can be, you can calculate with the units. To give you an example, if you are asked how many seconds is there in 1 year, of course I'm sure you know this immediately, but I want you to do it in the following way, because that tells you how you can calculate with the units as if the unit is a number. So you would write 1 year is equal to 1 year divided by days. But once you have written that, you have to do this. This is correct, because these days too would cancel each other. But you can write the days divided by hours. You have to write this again. So these hours cancel each other, the days cancel each other. So it's an identity. But you can hours, you can have minutes. And you can write seconds. and write seconds. It's important that if you treat these units as if they were numbers, they cancel out correctly. Now you immediately know 1 year divided by this 1 year divided by day is 365. Days divided by hour is 24. Hour divided by minutes is 60. Minutes divided by second is 60. And you still have the second here. So now you know how many seconds. This is of course trivia, but what I want you to learn is that you must treat the units correctly, so that I think this explains to you how you treat the units correctly. And when you get to complicated problems in physics, you have to remember this rule. We are going to adopt the MKS system. MKS means meter, kilogram, second. When I was a freshman student, the internationally adopted system was called CGS. That is centimeter, gram, second. Which is of course deeply related to the MKS system. But something like 30 years ago or so, internationally, everybody now adopts the CGS system, the MKS system. An important concept that you must remember is the significant figures. This concept is extremely important for physicists and for all scientists. Namely, if I write 3.05, I want you to understand that that is not equal to 3.05. What is on the left side mathematically is equivalent to what is on the right side. But in physics, when I write 3.05, I mean it's between 3.04 and 3.06. When I write 3.0500, I mean it's 3.050 between 3.0501 and 3.0499. In other words, when you write a physical quantity down, the last figure has an uncertainty of plus minus 1. Therefore, these two numbers are approximately the same, but the number on the right is much more accurate than the number on the left. So these two are not identical in physics, although in mathematics they are the same. So that is called the significant figure. This one has significant figure up to the second decimal point. This has significant figures up to the fourth decimal point. I can write 3.05 Of course, 3.05 is equal to 305 times 10 to the minus 2. In this case, both sides are equal mathematically and physics-wise, because the last figure has a possibility of plus minus 1, and they are of course equivalent. You should read in the book the discussion about the significant figures. I want you to remember about the velocity of light. Velocity of light is is 3.0 times 10 to the 8th meters per second. This is a very accurate figure and is universally used. But a more accurate one is given in the book. It is 2.99 You see that it has 1, 2, 3, 4, 5, 6, 7, 8, 9. Nine figures of accuracy. The reason that one can write such a number down is because in the last 30 years it has been able to measure both time and distance so very accurately. This is a very precise number. Does anybody have any difficulties understanding my English? No difficulties. Good. There's a question that we have to discuss now, namely, how is the second defined? In the early days, the definition of a second was using some sort of a clock. But of course, a clock, even a very accurate clock, is not accurate enough by modern standards. So now it is defined on page 6 of the book. In the middle of the book is the definition. I'll read it to you. 1 second is the time taken by 9,192,000. No, it's 9,192,631,770 oscillations of the light of a specified wavelength emitted by cesium-133 atom. In other words, it's defined in terms of that many periods of a specific emission from cesium. Cesium has many isotopes. Cesium-133 is one of them. And that isotope emits many lines. There's one specific line which has been chosen internationally. And that many 6 billion something oscillations is defined as 1 second. So it is a very precise definition. Actually, if you want to be even more accurate, you have to further define that cesium atom has to be in vacuum. If the cesium atom is under pressure, the period may be slightly different. So when you get to such great accuracies, you have to be very, very precise. So that is the definition of a second, of the unit of time. Now, how about the definition of the unit of length? For that, read page 5. In page 5, there is a statement which says the meter is the length of the path traveled by light in a vacuum during a time interval of that many of a second, that much of a second. This is now the international definition. The reason that there are these somewhat complicated definitions is because we now have the means to make very precise measurements. Originally, more than 100 years ago, when there was an international convention about the international units, the distance, the centimeter, was defined as the distance between two marks on a ruler kept somewhere in Paris. That you can see cannot be very accurate, because if you have a mark, if you have two marks, the most accurate you can imagine is maybe a fraction of a millimeter. As time goes on, one realizes that that is not accurate enough. So therefore, the definition was changed. It was changed several times, and now it reached what we just read. The time measurement is the most accurate. So therefore, first you define the unit of time. The distance measurement is the next accurate. So one defines it by saying the distance is related, the unit meter is related to the amount of to the length traveled by light during a certain time period. So therefore, what we have, what I want you to read is unit of time defined. How is the unit of time defined? Then unit of length. Then the unit of mass. I want to emphasize here that the unit of that mass is not equal to weight. In daily language, there is confusion. We say something is 1 kilogram. When in physics, when you say something is 1 kilogram, you mean its mass is 1 kilogram. It's it's related to the number of atoms and the mass of each atom added together, including the electrons, and that's the mass. So mass is a measurement of the bulk, while weight is a measurement of the force. When you say that you weigh 50 kilograms, it means that the Earth attracts you with a force which we define as 50 kilograms. So mass is a measurement of the bulk, while weight is a measurement of a force. These two are related but different concepts. We are going to have more to say about this after we get to discussing the three laws of Newton. Any questions about what we have said up to now? About the units, about significant figures, about actually about everything in chapter 1. By the way, there is in the book, near the end of every chapter, there's a section called Review and Summary. For you to test yourself, read that review and summary. If you understand everything in that section, you have captured the essence of that chapter. So while you are studying that chapter, refer to that section, and after you felt that you are finished with the chapter, read that section again to assure yourself that you have gotten everything that there is in that chapter. By the way, if you read the handout, read the syllabus page. It tells you what is the textbook. The textbook I shall refer to as the HRW. You must have that book. Then there are the reference books, Feynman Lectures, 美国物理试题与解答第一卷，跟赵凯华、罗卫因所写的新概念物理教程力学部门。不过这三本书the relevant chapters I'm going to Xerox and give to you. I will assign you a number of exercises, around 7 or 10 every week, and you must hand them in next Monday. If you are late in handing in the exercises, your grades for that week will be discounted. And there will be a midterm 期中考试, a final 期末考试, and your final grade would consist of 30% of your exercise results, 30% from the midterm, and 40% from the final. That page also lists the office hours of myself and Professors Ran Dong and An Yu. So, for example, for this week, if you read the syllabus, I want you to read the Halliday textbook, chapters 1 and 2. Also familiarize yourself with the useful appendices A to G. Familiarize yourself does not mean that you have to remember it. It's just that you know that there are these appendices, and at the proper moment you know where to find, for example, an accurate expression for the velocity of light, or for the Planck's constant, or for a specific formula giving you an integral. If you just flip through the pages and sort of scan appendices A to G, those are very useful information for you. And then the first week's exercises are listed underneath A, B, C, D up to H. And as I said, you should do these exercises and give them to me next Monday. Okay, no questions? Then we go to chapter 2. Chapter 2 talks about motion along a straight line. It's a one-dimensional motion. Now we all are familiar with some concepts. After all, we travel around, we move around, and we ride in cars. So there is the concept of an average velocity. What is the meaning of an average velocity? If you are traveling along a line, you go from here to here, there's a distance between them. Let's call that distance delta x. The distance divided by the time. Delta t is the time interval. Delta x is the distance. By the way, is this pen too thick? Is it better to use a thin one?这个不好，这个没有墨了。用粗的还用细的？还用这恐怕也是粗的。我要的是粗的，不过这是粗的。这个好一点。So the distance traveled, the delta x, divided by the time interval of that motion, that is the average velocity. So this concept is elementary. Now, if I now take half of the time, so this is the average velocity during this interval. If I now say I only look at the same motion, but only look at this distance, then I get another average velocity. So you can have average velocity of this interval, this longer interval, or the average velocity in a shorter interval. If you now make that the interval shorter and shorter, you get when you go to zero distance, that velocity, average velocity is called instantaneous velocity. And that is what is important. So it is equal to limit of this average velocity as the interval goes to zero. If the motion has a uniform velocity, then it doesn't matter whether you take the average velocity of a long interval or a short interval. But if, for example, it's a curve that's accelerating, then the instantaneous velocity at the beginning is not the same as the instantaneous velocity later. So in general, the instantaneous velocity is not necessarily equal to the average velocity at any time. This quantity, when you take a ratio and go to the limit of infinitesimal intervals, that is a concept fundamental to differential calculus. And in differential calculus, one writes it as dx dt. If you have studied differential calculus, you would be familiar with this. If you have not, you will be learning it both here and in your calculus course within the next week or two. Does anybody know who invented the differential calculus? Differential calculus was invented by two people, Isaac Newton and Leibniz. Newton was born 1642. And Leibniz was born the birth of differential and integral calculus is a great event in the history of mankind. One of the reasons that the Chinese science, modern science, did not develop in China was because, for various reasons, differential calculus was never invented in China. Actually, after you have learned the differential and integral calculus, you will realize that it's the most elementary concept. It is the most natural concept. That is a general situation relating to many physical laws. Before you understand it, it may not be reachable. But after you understood it in a more precise manner, you realize that it is a very natural and very simple thing. And differential calculus is a very good example of that situation. Newton clearly used differential calculus to write his big book, and that book is universally regarded as the beginning of modern science. It's called Principia Mathematica. It was published in 1687. But a very strange thing happened. Although he clearly developed both differential and integral calculus, he did not use differential or integral calculus in his book. This is called derivative. dx dt is called the derivative of x with respect to t. Derivative is导数. If you look at the dictionary I gave you, derivative is 导数. dx dt is the derivative of x with respect to t. Newton, in his work leading to Principia Mathematica, clearly used differential and integral calculus. In fact, the book was, most of what was in the Principia was done 20 years before that. It was done in the year 1666. But it was delayed. The publication was delayed by 20 years, partly because he needs to prove the following. The Principia Mathematica produced a tremendous impact on mankind because it explained the planetary motion of all the planets around the sun and the motion of the moon around the earth. But in order to discuss, for example, the motion of the earth around the sun, he knew he had to deal with two spheres, a big sphere which is the sun, and a small sphere which is the earth. Now in his original calculation, he took the sun to be one point, a heavy point, and he took the earth to be a lighter point, but both of them are points, and one small point going around a heavier point. Then there's the question of okay, but the sun is not a point, it's a sphere. So he had to prove that when you have universal gravitation, the universal gravitational force between a small sphere and a big sphere gives you a motion which is the same as if those two were just points. This requires an integral calculus, and it took him 20 years before he completely satisfied himself that that was correct. But the thing which is very strange is that when he wrote the Principia Mathematica, he did not use differential calculus, he did not use integral calculus. The whole of Principia was written in terms of a language similar to Euclid's geometry. I'm pretty sure in high school you have learned geometry, and that geometry follows the style of Euclid. You start with some axioms, then you have some propositions, then you have proofs, and you have corollaries, etc., etc. Newton patterned his big important book exactly like Euclid in this style. Not only this, he tried to prove everything as if it's a geometrical problem. Because of that, for the last 20 or 30 years, very few people have really plowed through the whole book. Everybody knows it's a most important book, but it's too complicated because if you do things with differential and integral calculus, it becomes very simple. But if you don't use that and do it geometrically, it becomes very complicated. The great astrophysicist Chandrasekhar was born around 1910, so he was some 10 or 11 years older than I am. In his old age, he decided to understand precisely the geometrical arguments of Newton in the Principia. Chandrasekhar was very proud of this book. I didn't read it, but if you are interested, you could go to the library. I'm sure the library has a copy of Chandrasekhar's modern interpretation of what Newton has done geometrically in the Principia. Leibniz was a German mathematician, and he was not so much a physicist like Newton was. He was more a pure mathematician. And it is now believed that he independently invented differential and integral calculus. But he had correspondence with Newton. So there was great controversy about whether their discoveries were independent or not independent. And that became one of the great scholarly debates around the end of the 17th century. In earlier centuries, before the 20th century, the biographers, all biographers, tend to only say good things about a famous name. For example, there were biographies of Newton, and in these biographies, Newton was a great man, and he was almost perfect. But in the 20th century, but by the way, that is more or less the kind of style of biographers in China in ancient times. But starting in the 20th century, there is a new movement of biographies in the West. There began a style in which one tries to paint the whole person. And now there are many biographies which show that Newton, though a great scientist, was not a likable man. He was not a kind person. He was vindictive, and he was not a person who was well liked. And the controversy between him and Leibniz was one of the things that dominated the end of his life. If you go to the library, you can browse through some of the books which give details of the life of Newton. Now, one of the controversies between Newton and Leibniz was what symbol to use for the derivative. dx dt is the derivative of x with respect to t. That is the notation of Leibniz. It was not the notation of Newton. Newton did not use the word derivative. Newton called it the fluxon. Today nobody uses the word fluxon, and the notation of Newton was very awkward, while this dx dt notation is very convenient. So today everybody uses Leibniz notation.是几点钟？他是不是也要响铃？
但是他这没响，他这个铃没响，可能坏了，我们可以休息一下。
Okay. Okay, so we'll have a 5-minute recess and then reconvene. 好，大家请坐下啊。我要问一个问题，就是哪一位如果觉得你懂了我80%讲的英文，就是我刚才讲的英文，如果你懂了80%，请你举手。
刚刚杨先生讲的话，英文讲的话，中间你能够听懂80%的，请举手。
所以不到的一半的人，远不到一半的人可以懂80%。OK， 那我想我得要改变一个办法，我多半讲中文，然后慢慢的希望你们可以，就是我讲英文的比例慢慢的增加，不过从开始我多半讲中文，这个也是一个习惯的问题。还有刚才有一位同学跟我说，他没有懂，比如说是25.4， 乘10的2次方，这是等于254。这个大家都懂吗？这个乘方叫幂，是不是？啊，这个，假如你要不习惯的话，你最好跟同学去讨论，这非常简单的，这个你必须要熟悉。对于刚才所讲的平均速度，刚才所讲的average velocity，average 就是平均 ，average velocity 就是平均速度，这个我想大家都懂的。那么把这个平均的速度，这个平均速度是说在这一段里头的平均速度，在其中一半的这地方有另外一个平均速度。假如这个速度是均匀的话，那这个大距离之间的平均速度跟这小距离之间平均速度是一样的。可是假如它不是一个均匀的运动的话，那么你不同的间隔不同的 interval 的话，得出来的平均速度就不一样。你把那个 interval 变得无限小，就变成那个时候的瞬时速度 instantaneous velocity。所以这两个观念很重要，一个是 average velocity， 一个是 instantaneous velocity。一个 average velocity里头是好多 instantaneous velocity 合起来，那么这个底下怎么做法，我们将来还要讨论。而这个 instantaneous velocity 的 notation 是 dx dt。刚才讲了半天，其实就是这两句话是主要的精神。Okay, now we'll go to uniform or constant acceleration. Acceleration 是加速，我们先得要问什么是加速。加速的意思就是假如一个人从这点走到这点，他在这里头每一点，刚才我们讲都有一个 instantaneous velocity 瞬时速度，可是它这速度不一定是一样的。你比如说是一个球从上面掉到下，大家都知道它是越走越快。那么所以在它这个过程之中，从楼上掉到楼下这过程之中，在每一点它的速度都不一样，是越来越快。那所以我就可以问，说是比如说是在离地1尺高的地方到地面这中间这1尺之间，它的平均速度是什么？就是它有一个它有个速度，有一个平均速度，这个平均速度跟 instantaneous 速度这个观念我们已经有了。可是假如我现在画出来，这面是 x， 这面是 t。假如一个人，这是 t 1秒、2秒、3秒，这1个 meter、2个 meter、3个 meter。假如有一条线，这是一条直线， 这样子的一个运动，你能不能告诉我它的是有什么特点？它是有一个固定的 instantaneous velocity， 就是叫做均匀速度的运动。为什么呢？因为它第一秒钟走了1米，第2秒钟又走了1米，第3秒钟又走了1米，所以它这个运动是一个均匀的。换一句话说，它没有加速。像这样子的一个运动是没有加速的。怎么样一个运动是加速呢？就是它越走越快。所以呢，比如说是这样子一个运动，它这样子就有加速。为什么呢？因为它第1秒钟的时候，它只走了第1秒钟只走了这么一点距离，第2秒钟呢，它是从这儿走到这儿，你看，第3秒钟呢，第1秒钟走了这一段，第2秒钟走了这一段，第3秒钟走了这一段，所以它的速度是在那儿是越来越快的，所以这个是一个加速的情形。向上这样子叫加速，这个用算学的语言，这条线叫做 concave upwards， 就是向上弯。假如它是这样子的话，这叫 concave downwards。你如果把它1秒1秒这样子的话，你就看见它第1秒钟走，第2秒钟走这么，第3秒钟走，第4秒钟走，就是越来越少，所以它就是速度是在降低的。所以你画出这个线是向上这样拱的话呢，就是个加速的运动；向下这样拱的话呢，就是个减速的运动。这又要注意，假如你把这个再延长出这样的话呢，你在底下一个的话呢，它比如说根本不动了；你再到一个的话呢，它是向下走，那个还是减速，不过是本来是速度，比如说是向上，是1秒钟走1米，后来1秒钟只走半米，后来1秒钟只走1/4米，这过了几秒钟以后，它根本在那1秒之间它不动了。就是不是不动了，就是它没有走任何距离，然后再的话呢向下走，那就是它的速度变成负的。这种样子它是减速运动。Decrease in velocity， decrease in velocity， 这个 velocity 这个数目不单是正的，也可以是负的。所以你假如我把一个球抛上去，然后它掉下来，它的这个速度是向下的，那么是越来越厉害。那它向上的时候呢，假如你把这个坐标是向下，我现在又在给你们引进了一个新的观念。就是速度可以有正负号。假如这个叫 y， 这个叫时间，我把一个球向上扔，那在开始的时候 dy dt 是1秒钟走1米，然后很显然它就越走越慢，所以这个图是这样的。我们将来要讨论这个线啊，大家晓得不晓得？这个 y 一个球扔上去，这是 t， 你们晓得不晓得这条线叫什么名字？叫抛物线 parabola。这个我们等会儿要仔细讲的。不过我现在要告诉你，就是它在这儿的时候，它的速度是正的，它的 dx dt 是正的。到了这一点的话，它的 dx dt 是0；到了这一点的话，它的 dx dt 是负的。就是它的 instantaneous， 它的瞬时速度在这儿是正的，在这儿是0，在这儿是负的。这个其实你一看你就懂，就是向上走的，它那个瞬时速度就是正的。在这点是平着的时候，它瞬时速度就是负的，就是0。到了这一点的话，它瞬时速度就是负的。这个你必须要能够你了解到一个程度，是你一看立刻就知道这一点。那么假如我现在不 plot y， 我 plot 它的速度，就是 dy dt， 就是它的开始的速度。OK， 它开始的速度 dy dt 是1，在 t 等于0的时候 ，t 等于0的时候，它的速度是1米 per second。可是它后来越走越慢，到这一点的话呢，它就变成0了。从这点到这点之间呢，它是越走越慢。这个你要画出来的话，它是这样子。说是这个一个东西扔出去，它的这个dy dt 是一条直线，这叫做 constant acceleration。等加速。什么叫等加速呢？就是在这每一点，你还有一个，这是位置，这个图是位置，这个图是速度，这底下这图是加速。速度跟位置的关系是，这速度是 dy dt， 加速跟这个速度的关系是加速是 dy dt 再低一些，就是速度是位置的 derivative， 加速是速度的 derivative。这点大家都懂了没有？有没有人不懂？假如你对这有一点点问题的话，你最好下课以后立刻找一个懂的同学给你讲清楚了。这是最基本的观念，而且这个观念你必须要变成直觉的。那么在每一点上，它的 instantaneous velocity 事实上是什么呢？就是dy dt 了。事实上是 OK， 我现在在跟你讲的这个其实是微积分的最基本的观念。就是假如这个运动假如这运动是这样的，那么我现在要问在这一点呢，它的速度，它的从这一点到这一点之间，它的速度平均速度是什么？那好，这个是 delta t， 这个是 delta x， 在这情形这是 delta y， 就是从这儿到这儿，这时间 是 delta t， 因为这是 t， 它向上走了，这个距离是 delta y， 所以它这个平均速度就是 delta y 被 delta t 除，这等于什么呢？如果我在这画一条直线，变成一个三角形，这三角形有这个角，这个角我叫做西塔。这个直角三角形，这面是 delta y， 这面是 delta t， 这个角是西塔。那所以 delta y 被 delta t 是等于什么？跟西塔是什么关系？正弦 tangent。这是你在三角里头所学会的。所以你如果画这样一条线，这个角度呢就是 tangent theta。好，我现在如果把这点不动，把这个 delta t 缩小，把它缩小的话呢，我这个画不清楚的。这是刚才那三角形放大了。如果我把它缩小，比如说是 delta t 是一半的话呢，那就跑到这儿来了。所以这个就变成这样的。如果我拼命把这个缩到最后的话，我现在问问题说这条线变成什么？叫做切线。这切线是什么意思呢？就是你画了这条线，你们越走越近，它最后就变成这叫切线。那所以 limit of 这个，所以 dy dt 就等于什么呢？等于 tangent of 哪个角呢？是那个切线与 t axis 之角，对不对呢？因为这个 theta 就变成了这个切线。这个观念 tangent of 这个切线跟 t axis 之间的角，这个整个这个 tangent 又叫做 slope。为什么叫 slope 呢？就是要 slope 是什么意思？是坡度，是不是中国翻成什么？是不是叫坡度？slope 我就用 slope 这个字。你如果上一个坡，那个坡就叫做一个 slope。那么在数学里的这个 slope 这一句话呢，就是讲这个 tangent。所以你如果看见一条线，画了这条线，你到在那一点它有个切线，切线就是在那个时候它要向什么方向走。那么那个切线它的跟t axis 之间的那个角的 tangent 就是在那个地方的 derivative。 你懂了这点以后，你就知道这个运动在这儿，它的 tangent 因为它的 theta 是一个比如是20度，走到这儿这个 theta 变小了，所以 tangent 也变小了。它如果这线如果走到这儿的话呢，它 tangent 是这样的， tangent 是这样，那 theta 就变成是 0。所以 tangent of theta 就是 0， 所以在这点 slope 等于 0， 在这一点呢，它的 slope 变成负的，因为那个角是跑到底下去了，那个 theta 是变负的。所以事实上这个观念，这个 tangent 这个 derivative 这个观念是非常简单的。如果有一个 curve， 那么在这点它的 slope 向上，所以是正的。它的 slope 是正的，在这点 slope 是0，在这点 slope 是负的，在这点 slope 又是0，这 slope 又是正的，这 slope 又是0，又是负的，又是0等等。那么你懂了这个所以这个是位置的图，位置 对于时间的图，这个是它的速度。那么这速度在这一段是正的，所以是正的。到这一点这速度是0，到这以后呢，这速度变成负的了。那么这 dy dt 呢，就是这个东西的 slope， 这个东西的 slope 永远是一样的，因为它的 tangent 老向一个方向，所以这个 dy dt 呢是一个负的数目，而且是一个固定的数目，所以它对于时间讲不改，所以加速是这个图。刚才我讲的这3个图，大家懂了没有？这个你如果没懂的话，我建议你去找一个同学，要弄得绝对的懂。在伽利略以前，大家对于这个一个掉下来的东西的速度不清楚。为什么那时候不清楚呢？比如大家知道有名的就是说是伽利略从比萨斜塔上头放下2个东西，一个是重的，一个是轻的。那么要问呢，说是到底下是不是一块到的底下？那么这个在那个以前呢，我想中外都是有一个印象，是觉得重的东西先到地，轻的东西后到地。它证明不是这样的，是2个一块到底。那为什么以前有一个错误的印象呢？有人会回答我这个问题，不会。为什么以前有个印象，觉得重的东西要先到地，轻的东西后到地？因为有空气的阻力，有空气的阻力，所以假如你用一个很轻的东西的话，你用很轻的气球的话，它根本掉得非常之慢，所以当然它是后到底。所以在以前的话呢，没有了解到有空气的阻力的影响。伽利略所做的事情呢，是他用了2个不一样重量的，可是都是相当重的，所以这个空气这个阻力在他的实验里头呢，不是一个重要的因素。那在这种情形之下，他就证明说2个是一块掉下来的。所以他就证明出来了，假如空气的阻力不重要的话，这个掉出来这个东西是像这样子的 motion， 是一个你要把它画成这个位置的话是一个 parabola， 你要画成速度的话是个固定的速度，你如果把它画成加速的话，这加速是一个固定的负的数目。这个是在伽利略以后才发现的。今天这个当然很容易做这个实验，因为那时候量时间比较复杂，你通常你要把一个球放到地下，这个很短的一个时间它掉到地下，所以你很难量。那今天呢，用很简单的方法就可以量得非常准确，就知道确实是加速度是一个固定的，而这个加速度的数目你们要去书上看，要记住这个数目，因为这个数目是非常重要的一个数目。底下我要讲这个等加速。要讨论等加速运动，uniform acceleration motion。假如在一个开始的时候，它的速度是 v0， original velocity。等 uniform acceleration 的意思就是说 for every unit of time the velocity is increased by a certain amount a. A is equal to uniform acceleration. Uniform 就是均匀的。OK， 那如果 if the original velocity is v0, what is the velocity after 1 second? What is the velocity after 2 seconds? Therefore, the velocity after t seconds is you might say that's the definition. 这就是等加速运动的定义，就是说原来的 velocity 是 v0， final velocity is v。Final 就是最后的速度是 v， then the final velocity is equal to v0 plus a times t. This is you might say this is the definition of uniform motion. Okay. Do we know what is the distance traveled? What is the distance traveled in t? The distance traveled 就是 x。我现在不讲y 了，我讲横的x 减去 x0 是原来的位置 ，x 是后来的位置 ，so x minus x0 is the distance traveled during the period t。这个很容易算 ，because the initial velocity is v0。Final velocity is v0 plus at. This is initial velocity. This is final velocity. So what is the average velocity? Average velocity is the average of these two numbers. So it's v0 plus v0 plus at divided by 2. That's the average velocity. Average velocity times the time is the distance traveled. Therefore, the distance traveled is equal to t times this quantity. Which therefore is equal to Does everybody understand what we just did? 所以现在有两个重要的公式 This is one formula. This is another formula. This formula gives you the final velocity. This formula gives you the distance traveled. This may sound very simple, but actually we have made an assumption. The assumption is that it's a uniform acceleration. If it were not a uniform acceleration, this average velocity calculation is not correct. The reason that, no, the average velocity is always this. The average velocity is always equal to the average velocity Can somebody tell me? 假如它不是一个 uniform acceleration， 我刚才讲的这里哪一步不对了？OK， 我们来复习一下。假如它不是个 uniform velocity， 也不是 uniform acceleration， 那这个 formula 先不对了，因为这个 formula 就是 definition of uniform acceleration。假如所以这个 formula 先开始就不对了。然后呢，这个 formula 当然也不对，可是这个 formula 精神说是把 initial velocity 加上 final velocity 被二除，就是 average velocity， 这对不对？谁赞成是对的？谁赞成是不对的？好，这是不对的，因为这个anyway 你要觉得不对就对了，这个因为它是 uniform 的 acceleration， 所以这才对，所以才会有这个公式。OK， 底下位置使得你知道你是不是懂了。我给你一个习题，这习题是用这两个公式，有两个放在方块里的这公式，用此二公式证明说是 v square 减去 v0 square。有了那两个公式，你很容易证明这个。这个你们不需要教这个题目。这个不过if you do this exercise, you would understand the thing better. I think we are going faster than I originally thought we would go. So I will see whether the exercises that you are going to hand in next Monday 证明说是你们都没有问题。假如是下一个礼拜一的这个 exercise 结果很不好的话呢，那么我们得另外想办法。假如是很好的话呢，那我想我们可以用这个速度继续下去。事实上，这样厚的这一本书里头的内容很少。这刚才所讲的这两个公式，你要是懂得它的来源，那么会应用它的话，基本上这个这第二个 chapter 里的东西你都已经懂了。就 as I said before, at the end of every chapter 是有 review 跟叫做什么review and summary。你们应该把那 review and summary， 你要想知道你对于那章是不是完全懂了，你就把 review and summary 拿来仔细看看。I hope as time goes on, you will understand my English better and better. As I said, these days English becomes a sort of a international language for science. So it'd be very important for you to brush up your English as fast as possible. 在这个 Syllabus 上面有我的办公时间，也有他们阮教授跟安教授的办公时间，所以你们如果有问题的话，可以去找我们。Okay, good luck.
昨天有学生问，如果说要去见你的话，需要跟你预约吗？
我想开始不预约，我们看将来是怎么一个状态。
开始不用。
假如人多了的话，那再讲好了。